What is the universe made of? If you said matter, atoms, particles, stuff you can touch, physics has some bad news. Because over the last 80 years, every branch of physics, from thermodynamics to quantum gravity to cosmology, has converged on the same unsettling answer. Everything is made of information. And the evidence isn't speculation. It includes the most cited paper in the history of physics, a Nobel Prize, and an equation that cost Stephen Hawking a 40-year bet. In 1948, a mathematician at Bell Labs in New Jersey did something no one had ever done before. Claude Shannon single-handedly created the field of information theory. His paper, A Mathematical Theory of Communication, did something revolutionary. It defined information as a quantity, not as meaning, not as knowledge, as something you could measure, like temperature or pressure. His equation, Shannon entropy, tells you the average amount of information in any message. A coin flip carries exactly 1 bit. A dice roll carries about 2.5. The English language, with all its redundancy, carries about 1 bit per letter. 2 more results made Shannon immortal. His source coding theorem proved you can compress any data down to its entropy, and no further. His channel capacity theorem set the absolute speed limit for reliable communication through noise. Every phone call you make, every video you stream, every GPS signal that finds your car, all of it runs on Shannon's framework. He didn't just describe information. He gave humanity the math to build the digital age. But Shannon's information was abstract, a mathematical concept floating free from the physical world. In 1961, someone proved it was real. Rolf Landauer was a physicist at IBM when he asked a deceptively simple question. What happens, physically, when you erase a bit of information? His answer, published in 1961, changed the relationship between information and physics permanently. Erasing 1 bit of information releases a minimum amount of energy, kT natural log of 2. At room temperature, that's about 2.87 times 10 to the negative 21 joules. Tiny, almost immeasurably small. But not zero. For 50 years, this was a theoretical prediction. Then, in 2012, Antoine Bérut and colleagues at the École Normale Supérieure de Lyon verified it experimentally, at the single-bit level, using a silica bead trapped by laser light. Information is not abstract. It's not metaphorical. Erasing a single bit of it heats up the universe. Shannon told us how to measure information. Landauer proved it matters physically. And what Bekenstein discovered next changed what we thought reality was made of. In 1973, a young Israeli-American physicist named Jacob Bekenstein was staring at black holes, and he noticed something that didn't make sense. According to thermodynamics, every physical system has entropy, a measure of its information content. Bekenstein calculated the entropy of a black hole and found something shocking. It wasn't proportional to the volume. It was proportional to the surface area. Repeat that. The information inside a black hole isn't stored in the 3-dimensional interior. It's encoded on the 2-dimensional boundary. A solar mass black hole has an entropy of roughly 10 to the 77th. That's a 1 followed by 77 zeros in units of Boltzmann's constant. All of that information living on the surface. Bekenstein also derived something called the Bekenstein bound, a physical upper limit on how much information any region of space can contain. It depends on the region's size and energy, and it's not a theoretical nicety. It's a law of nature. In 2003, Bekenstein wrote it plainly in Scientific American. The physical world is made of information, with energy and matter as incidentals. But if information is stored on surfaces, and information is physical, and information has a maximum density, then what happens to all that information when a black hole evaporates? That question started a war in physics that lasted 40 years. In 1976, Stephen Hawking dropped a bomb on physics. He showed that black holes aren't fully black. They emit a faint thermal radiation, now called Hawking radiation. Over immense timescales, this radiation causes the black hole to slowly evaporate. Eventually, it vanishes entirely. And here's the problem. That radiation is thermal, random. It carries no information about what fell into the black hole. So if you throw a book into a black hole, wait for it to evaporate, and collect all the radiation, you can't reconstruct the book. The information is gone, destroyed. Except, in quantum mechanics, information can never be destroyed. That's not a suggestion. It's a mathematical law called unitarity. Hawking was saying that gravity breaks quantum mechanics, and physics divided into two camps. In 1993, Don Page, Hawking's former student, derived what's now called the Page curve. It shows exactly how the entanglement entropy of the radiation should behave if information is preserved. It rises at first, hits a peak halfway through evaporation, then falls back to zero. In 2012, the AMPS team, Almeri, Marolf, Polchinski and Sully, proved that saving information creates a new problem, a firewall of infinite energy at the event horizon. Either information is lost, or the smooth horizon is lost. Pick your crisis. And then in 2019, everything changed. Two independent teams, Jeffrey Pennington at Stanford and Ahmed Almeri's group, discovered the island formula. Using a mathematical tool called replica wormholes, they showed that standard semelic gravity, with no exotic additions, naturally reproduces the Page curve. The information gets out. The universe never loses a single bit. Think about that. The universe fights this hard. 40 years of the greatest physicists alive arguing over it, to preserve information. Not energy, not matter. Information. Bekenstein's discovery, that black hole information lives on the surface, wasn't just about black holes. In 1993, Dutch physicist Gerard 't Hooft proposed something radical. What if it's true of all space? What if the information describing a three-dimensional volume is always encoded on a two-dimensional boundary? Leonard Susskind at Stanford formalized this in 1995. They called it the holographic principle. And then Juan Maldacena proved it. In 1997, Maldacena, an Argentine physicist at the Institute for Advanced Study, published a paper that has since received over 25,000 citations. It is the most cited paper in the history of high-energy physics. What he proved is called the ADS/CFT correspondence. In a specific type of spacetime, anti-de Sitter space, he showed that a gravitational theory in 5 dimensions is exactly, perfectly, mathematically equivalent to a quantum field theory living on its 4-dimensional boundary. All the physics, all the gravity, all the motion, all the information encoded on the boundary. The interior is a hologram. Now, a critical caveat. This proof works in anti-de Sitter space, which has a negative cosmological constant. Our universe has a positive one. So we can't say our universe is holographic, yet. But in 2020, Andrew Strominger at Harvard launched a program called Celestial Holography, working to extend the principle to flat spacetimes like ours. It's early stage, but it's active. Either way, the mathematical fact stands. A lower dimensional surface can encode the complete information of a higher dimensional space. Reality can be a hologram. If information lives on boundaries, what is the space between them? In 2006, Shinichi Ryu and Tadashi Takeyanagi published a formula that connects geometry to quantum information. The entanglement entropy between 2 regions of a boundary theory equals the area of the minimal surface connecting them in the higher dimensional bulk. In plain English, the geometry of space is built from entanglement. More entanglement, more space between regions. In 2013, Maldacena and Susskind went further. ER equals EPR. Einstein-Rosen bridges, wormholes, are mathematically identical to quantum entanglement between particles. The connection that links 2 entangled particles across the universe is a wormhole. Space itself is sewn together by quantum information. And this isn't only theory. In 1982, Alain Aspect experimentally confirmed Bell inequality violations, proving that quantum entanglement is real, not a mathematical artifact. In 2022, the Nobel Prize in Physics was awarded for loophole-free demonstrations of exactly this result. Space isn't a container for information. Space is information. Remove the entanglement, remove the space. The observable universe stretches about 93 billion light-years across. It contains roughly 2 trillion galaxies and 10 to the 24th stars. All of this matter isn't randomly distributed. It's organized into a cosmic web. Galaxies clustered into nodes, connected by filaments of dark matter, separated by enormous voids. The Laniakea supercluster alone contains 100,000 galaxies and spans 520 million light-years. In 2020, Franco Vazza, a cosmologist, and Alberto Feletti, a neurosurgeon, published a paper in Frontiers in Physics that should have been front-page news. They didn't just compare the cosmic web to a neural network, they measured them, quantitatively. Same fractal dimension, 1.7 to 2.0. Same network topology, scale-free, small world. Same connectivity distribution, same node-to-filament ratios. The entire observable universe and a slice of mouse brain organize themselves identically. This is not a metaphor. It's measured data, published in a peer-reviewed journal. The universe at its largest scale, and the organ that lets you perceive it, share the same architecture. As if information is organizing itself the same way regardless of scale. And it's not just physics. Biology is information technology. DNA is a 4-symbol code: adenine, cytosine, guanine, thymine. Each base pair carries 2 bits of information. Your genome is about 3.2 billion base pairs, roughly 800 megabytes of data. And the error correction is extraordinary. After proofreading and repair, DNA replication makes about 1 error per billion to 10 billion base pairs. That's more reliable than any hard drive ever manufactured. Information being encoded, copied, transmitted, error corrected for 4 billion years. Life doesn't just use information, life is information, reading itself. So physics says the fundamental substrate is information. Biology says the mechanism of life is information processing. And now we reach the deepest question. Is information everywhere at once? In 1952, David Bohm proposed an alternative to the standard interpretation of quantum mechanics. In Bohm's theory, particles have definite positions at all times. They're guided by something called the quantum potential, a field that carries information about the entire system, every particle, every location, simultaneously. And this quantum potential is non-local. A particle's motion depends on what every other particle in the universe is doing, regardless of distance. Information connects everything. In 1980, Bohm expanded this into a philosophical framework. What we call reality, objects, separations, locations, is the explicate order. It unfolds from a deeper level he called the implicate order, an enfolded wholeness where everything is interconnected. Like a hologram. Break the plate, and every fragment still contains the entire image. The information isn't stored in any one place, it's folded into everything. Bohm's theory reproduces every prediction of standard quantum mechanics perfectly. It's a minority interpretation. Most physicists default to Copenhagen. But experimentally, it's never been wrong. And there's one more experimental fact that reinforces this. In 1959, Yakir Aharonov and Bohm predicted that electromagnetic potentials, not forces but the information-carrying fields themselves, directly affect physical outcomes. It was confirmed experimentally, and it's now called the Aharonov-Bohm effect. The fields that carry information shape reality, even where no force is present. In 1941, a German engineer named Konrad Zuse built the first programmable computer in his parents' living room. 28 years later, he was the first person to propose that the entire universe is one. Zuse's 1969 book, Rechnender Raum, Calculating Space, argued that the fundamental substrate of reality isn't matter or energy, it's computation. Space and time are discrete. Every interaction is calculable. In 2003, philosopher Nick Bostrom at Oxford formalized this intuition into a logical trilemma. At least one of these 3 things must be true. 1. Civilizations go extinct before they can create simulations. 2. Advanced civilizations choose not to run them. 3. We are almost certainly living in one. And certain features of our universe are suspiciously consistent with option 3. The Planck length, 10 to the negative 35 meters, looks like a pixel size. The speed of light looks like a maximum processing speed. Energy comes in quantized packets, like digital data. Seth Lloyd, a quantum physicist at MIT, takes it further. The universe doesn't resemble a computer, it is a quantum computer. Every elementary particle registers bits. Every interaction processes them. The universe computes its own evolution. But let me be clear about the evidence tier here. Sabine Hossenfelder calls the simulation hypothesis unfalsifiable. A fun idea, not a scientific theory. Sean Carroll points out that simulating continuous quantum fields requires infinite precision. And there's the infinite regress problem. Who simulates the simulators? This is Tier 3 territory. Logically valid, empirically untestable. But here's what is testable. Whether we're in a simulation or not may be the wrong question. The right question is, why does reality have so many features that look computational? In 1960, physicist Eugene Wigner published an essay with one of the most famous titles in science: The Unreasonable Effectiveness of Mathematics in the Natural Sciences. His question was simple. Why does mathematics, a human invention, describe physical reality so perfectly? And not just describe it, predict it. Dirac's equation predicted antimatter 4 years before anyone found it. Maxwell's equations predicted electromagnetic waves 23 years before Hertz confirmed them. General relativity predicted gravitational waves 99 years before LIGO detected them. And mathematical truths are independent of culture. The Pythagorean theorem was discovered independently by the Babylonians around 1800 BCE, the Indians around 800 BCE, the Chinese around 300 BCE, and the Greeks around 500 BCE. Same truth, different continents, different centuries. In 1931, Kurt Gödel proved something even more disturbing. Any formal system complex enough to express arithmetic contains true statements that cannot be proven within that system. Mathematical truth transcends any finite description. If math is discovered, not invented, then the universe has always been information. It didn't need us to write it down. And here's where it all converges. John Archibald Wheeler, the physicist who named black holes, wormholes, and quantum foam, the man who mentored Richard Feynman, spent the last decades of his life on one idea. It from bit. Every it, every particle, every field of force, even the space-time continuum itself, derives its function, its meaning, its very existence entirely from the apparatus elicited answers to yes or no questions, binary choices, bits. Wheeler's delayed choice experiment, which has been performed multiple times, demonstrates that the observer's decision to measure a photon's path, made after the photon has already passed through the apparatus, retroactively determines its history. The choice you make now shapes what happened then. Without observation, there is no fact. The universe isn't a machine running in the background. It's information waiting to be read. But if the universe is information, then something has to read it. Something has to decode the signal. And that something is consciousness. So here's where we are. Shannon quantified information in 1948. Landauer proved it's physical in 1961. Bekenstein showed information has a maximum density in 1973. And it's stored on surfaces, not in volumes. Hawking fought for 40 years, and the answer is, information is never destroyed. Maldacena proved that reality can be a hologram, with 25,000 citations backing him up. And Vazza and Feletti showed that the cosmic web and the brain are structurally identical. The universe is made of information. But information without a decoder is just noise. Something has to read it. And that reader is your brain. Except, what if your brain isn't generating consciousness? What if it's filtering it? What if the brain is a reducing valve, and most of reality is being hidden from you on purpose? And what if, when the filter comes off, you see everything? That's not philosophy. That's what the data from dying brains suggests. In a future episode, we ask, does the brain generate consciousness, or is it a reducing valve? And what happens when the valve opens? That's next.